Good afternoon, Physics 20. Hope you guys are all doing well today. Yes, two videos, one day, filmed one this morning, one afternoon. In case you picked up on the contextual clues, like I'm wearing the same shirt, for example. Anyway, ladies and gentlemen, welcome back. Free falling objects. Awesome, awesome topic. This is a ton of fun. I love this one. Now, FYI, ladies and gentlemen, this is the last video for Chapter 1 of your first unit on kinematics. So what that means is that A, if we are in the classroom and doing quizzes, you have a quiz after this topic. B, if, you have an assignment due. 2, if we are not in class and we're online, you have an assignment due. So keep in mind, depending whatever scenario we are with where COVID is and whether we're shut down or not, will depend on what assessments you have. But either way, you have an assignment due coming up, so get her done and see me if you have any questions. And 2, if we are in class, we absolutely have a quiz coming up. Cool beans? Cool beans. So today we're looking at free fall. So stuff falling. Okay. Today's video, we're going to be looking at two cases. If we're going to be taking something and dropping it, or if we're going to be throwing something up and it comes straight back down. We'll be looking at two-dimensional vectors up and coming later. That's chapter 2. So I have borrowed from my dog, who you've probably heard about, at least Freya, in the later videos, the stuff I filmed during the school year. Because I started filming in dynamics, right? Because when COVID shut down back in March. You can see this like dog snoot coming up into the screen right around here, and hear all sorts of barking and crazy dog things. And yeah, she's a nut. But she's at daycare today, so sorry guys, no puppy in today's video. But I nicked one of her toys. A favorite, a yellow tennis or orange tennis ball. Oh, the rage when you're a dog. So this is going to be our, what's the term I'm looking for? Demo today. It's going to be throwing dog toys. All right, so enjoy the pun or the meme. I think it is true. You know, when you're awake in the morning, waking up first thing, just don't want to get out of bed. All right. So, ladies and gentlemen, free falling objects. So once again, the two things we're going to be looking at are dropping objects or throwing them straight up in the air and catching them again. So that's going to be what we're focusing on today. Okay. And what we've got is notes. Make sure you have your notes handy, stuff to write with. Pause the video as we're going through when you need to write stuff down. All right, so when an object is allowed to fall to Earth, it is in free fall, okay? And once again, your acceleration is going to be 9.81 meters per second squared if you ignore air resistance. The curriculum objectives for Physics 20 say ignore air resistance. So we are going to ignore air resistance. Now, in reality, is air resistance ignorable? No, it isn't. After this video, I'm going to go and film the next one, which is the field trip for this particular topic. So I'm going to go into the kitchen and I'm going to drop a textbook and some paper, and we're going to compare what air resistance actually does. And we'll talk a bit more about some nuances with gravity there. But for now, we are going to ignore air resistance. Okay, so that is what you need to know for air resistance in high school. Is it actually a thing? Yes. When you go to university and start engineering, is air resistance going to show up? Mm-hmm. So it's something you're going to need to know, but it's not in the high school curriculum. Sorry, guys. Okay. So our 9.81 meters per second squared, which is in your data sheet, so it's G 9.81 meters per second squared. Remember, these are the units. The meters per second squared is the units for gravity. Don't square it unless you have, it says in the equation, square it, which, generally have to square acceleration. Okay, it's the average on Earth. Now, that value does vary a bit between where you are on Earth and how thick the crust is, but we don't worry about that. We use 9.81. Okay. And if air resistance is ignored, so we'll talk more about this in the field trip video, which I'll film after this. So all of the objects are going to fall at the same rate, no matter what their mass is. Okay? So a bowling ball and a marble are going to hit the ground at the same time, right, when you drop them from similar heights. So watch for that video. I'll have put all these videos onto Google Classroom. So this video, the next video, which will be the field trip video, and then all the notes will be on that same page on Google Classroom. So go find that video. Or if you're finding this on YouTube, then it's the video numbered after this one. It should be like number 6 or something. All right. So ladies and gentlemen, acceleration due to gravity, it is a vector, so it has direction and magnitude in each direction. Now, gravity always pulls objects down, and we're going to talk about whether or not we want down to be positive or a negative number. It doesn't really matter, so long as you're consistent within that particular question. If you choose down to be positive, then up has to be negative. And every down vector needs to be negative or positive in that case. If you choose to make down negative 100% of the time, then you just need to be consistent and have everything that is up positive and down negative for that question. Cool beans? Cool beans. All right. So terminal velocity is the greatest velocity which an object in free fall can reach. And at the heights that we are looking at, it's going to be right before an object hits the ground, like just before it hits the ground. We are not talking about terminal velocity of, say, like skydivers or something. Okay. So we're all dealing with stuff that's really close to the surface of the Earth. That's what we're dealing with. And when you guys get to the circular motion, and when we're going to go into objects in orbit in space, then we're going to start talking about stuff that's farther out. All right, guys? Okay. All right. So vector arrows. So we've got an object dropped and an object thrown in the air. So I'm just going to jump full screen here. There we go. I'm full screen. Okay, I didn't discover this feature until, I don't know, what was it, like May or June, something like that. So I'll do this in videos now, but when you get to the dynamics unit, where I filmed all my videos back in March when the school shut down, I didn't discover this. I didn't even discover how to go full screen until a couple weeks in. It's just kind of funny, watching me learn how to use the tech. Situation normal. You guys are used to it by now. So here is my dog's tennis ball. Okay, so we're going to look at simply just dropping this guy. So we take the ball and we drop it. So let's think about the motion. Right up here, the moment I let go of the tennis ball, like that, just as I open the tennis ball, I open my hand and let it go. Is it moving? No, it isn't. It's stationary when you let it go. So what does that tell you about VI? VI is 0. The second you see the word dropped, VI is 0. Okay? So what's the value for G when you drop an object? Your acceleration. So A or G. You can use either A or G here, guys. So A or G is going to be 9.81 meters per second squared, and the direction is down. Okay, so those are the values you're always going to have with the word dropped. Now, when you drop the ball, we're going to be starting with your velocity. It's going to be going slow, but as it falls, it's going to be going faster and faster and faster because it's accelerating at a rate of 9.81 meters per second squared. Okay, I'm going to jump back down to the notes here, pop back down to the corner. And we're going to look at our vector arrows. Now we're going to be doing our, I forgot the mouse for the other computer. I've got stuff on like 2 computers going all at once. I feel really techy, even though I don't really know. I don't feel I'm really not that techy, but I feel techy with all these computers. All right. So ladies and gentlemen, your VI, when you're stationary, is going to be 0 meters per second, okay, right the second you drop it. So you're not going to have a vector arrow at that point because the object isn't moving. Well, at this next stage, its velocity is going to be increasing a bit, okay? And as it continues to fall, your velocity is going to be increasing even more, okay? Because as you're falling, you're accelerating. All right? Okay. So let's jump back full screen again here. We're going to talk about taking a ball, throwing it in the air, and then coming straight back down. And then we'll draw the vector arrows for that. So I've got my dog's tennis ball. I take it, throw it in the air, and I catch it. Okay? It's a good thing Freya's at daycare today. She would lose her marbles if I was playing with one of her toys. How dare I throw her ball if it's not for her? There's one physics video later on where I'm looking at like ramps and such, and she kind of rolling a ball down a ramp and that kind of thing, and she loses her wig. It's actually a really hilarious video. You'll get to enjoy that one later. So I take this one. Now, right the millisecond that the ball leaves my hand, when I'm throwing it up and catching it, the second the ball leaves my hand, just that moment it leaves my hand, that is going to be your initial velocity. Well, notice what happens as the ball goes up in the air. It slows down until it reaches its maximum height. At its maximum height, it's stationary for just a moment. It's stationary, right? It's not moving. So then, as gravity takes over, it's going to fall again. Okay, so gravity is pulling it down as the ball's velocity is slowing down, and then it's going to speed up when it hits the ground. Ignoring air resistance, the initial velocity the moment it leaves your hand is going to be the same the moment it reaches your hand. So we're going to talk a little bit about that more when we get into one of our calculations here. Okay, I'm back in the corner. So one other arrow I want to draw here is going to be our acceleration vector. So here, acceleration is still going down. What about the acceleration vector here? It's the same. So ladies and gentlemen, our gravity acceleration vectors are all going to be the same, right? So it's all 9.81 meters per second squared. Now, the same thing when we jump over here. Our acceleration vector arrows are all going to be the exact same size the entire time here. All right, so A is still going to be pulling down. Gravity is still going down. Like, we don't care where we are in this. Our acceleration is constantly down at 9.81 meters per second squared. It's our velocity vectors that are going to be different. So what happens is when you are initially starting here, your VI is going to have a numerical value. Your velocity is going to be at its maximum initially. But then as the ball, because you're going up, notice your velocity arrow is up, but your acceleration arrow is down. So you're going to be slowing down. So that means that your velocity vector here is going to be smaller. That ball is slowing down as you throw it up in the air. Well, when we get up here, the velocity up here at the top is 0. Okay, it's not moving. Okay, and now these two are in the exact same position. Now, I technically the ball doesn't go up and go down like that. We'll often draw it like that because it's easier than up and down. But the actual motion is up and straight down. That's what we're doing math with, is up and straight down, up and straight down. Where we have an arc like this, that is where we're going to be getting projectile motion, which is what we're going to be looking at later. And then that's a pretty huge part of this particular unit. It's awesome. I love projectile motion. I really hope we're in class for projectile motion, because then I get to throw footballs around. It's fun. Just throw a football around class. I'll disinfect it first, and whoever I'm throwing a football with will hand sanitize, and then we'll throw the football. Awesome lesson. Awesome. Okay, so we need to draw the rest of our vector arrows here. So this guy is still at the very top. His velocity up here is going to be 0. Well, now the ball is falling down, so it's now acceleration is still the same, still 9.81, but its velocity is going to be picking up a bit. When it gets down to here, its velocity is going to be the same magnitude as it is here, but just opposite directions. Sounds good, guys? Okay. Once again, lesson subtle hint on test. I'm fairly certain I give you at least one of these in written response on your quiz. Lesson subtle hint. Okay. So let's go and look at how to do the math with this. Now, I am going to write a tip down here for you guys. Anytime you're doing freefall calculations, what category of equation must you use? Acceleration. You must use acceleration equations. Okay? You do not use v equals d over t. That is for uniform motion. Anything free falling is not uniform motion, guys, okay? Free falling is not uniform motion. So if I see v equals d over t on a free fall question, I'm going to cry inside. I'm going to be sad. Don't make me sad. Use acceleration equations. Now, remember on your data sheet how I had you guys highlight stuff and I highlighted these equations in pink? You see these pink equations? Okay. Those are the equations that you can pick from in order to do free fall questions. Do not use v equals d over t. That is for uniform motion only. Okay? Okay. Now remember, there are two values in these questions that I am going to either imply or give to you indirectly in other terms. Now those are going to be VI or VF, depending on your scenario, and gravity. So the second that you have a free fall, so thrown up and comes back down, or you see the word dropped, I am going to be implying one velocity, either VI or VF, and gravity. Now, gravity is going to equal your A. G is going to be A. So do not look for G on your data sheet in those equations. It's not going to be there. It's going to be A. G is just a fancy letter to represent the acceleration of gravity. Okay? So A in this case is going to be 9.81. And your velocity, either VF or VI, is going to be 0, depending on if you're dropping it or throwing it in the air. Alrighty-o? Alrighty-o. So, let us begin. A large steel ball is dropped off a top shelf. Pause. Dropped. Okay? We take a ball, we drop it. Take a ball, we drop it. We've dropped the ball. What is the initial velocity? The millisecond I open my hand. 0. The second you see the word dropped, that is going to tell you that your VI is equal to 0 meters per second. Once again, I did not give a numerical value with stationary or 0 meters per second. So that means that 0 does not count towards your sig digs. Okay. The other values will. Okay. All right. So, ladies and gentlemen, what does this also tell you? There's another number that word dropped gives you. 9.81. By saying that we've dropped something, that means that something is falling and gravity is pulling it. Unless you're on Mars, or some other planet, and I don't say what the value of the acceleration due to gravity is on that planet, you use 9.81 meters per second squared. Now, I'm pretty certain I don't do that. Okay? We don't go to other planets here. Well, not until our third unit anyway. All right. If the ball hits the floor with a velocity of 11.7 meters per second. Okay, well, that is our final velocity. What is the height of the shelf? Now, height is scalar. Okay. What other is another term we could use for height? What's another letter? Distance. The definition of height is how far something is from the bottom to the top. Like if you look at my bookshelf here, the height of the bookshelf is from the definition from the bottom, is the distance from the bottom of the shelf to the top of the shelf. Decently sized bookshelf. You guys can't even see the bottom two shelves on the screen there. Okay. So this is where you have to think carefully about each of the meaning of these words is. As a height, the definition of height is the distance from the bottom to the top of the shelf. It's the distance in which the ball is going to fall. So you have been asked to calculate D. You're not going to find H on there. Okay, you're not going to find H in those acceleration equations, but you'll find D. So we have D, VF, VI. Well, when you look at your equations on your data sheet, you are going to see that our equation is VF squared equals VI squared plus 2AD. So you're going to write out your equation. That's the first thing you're going to do. Now, let's make our lives easier. VI is 0. Just cancel that out and make it 0. Okay? So VI squared is 0. 0 plus 2AD is equal to 2AD. Okay, so watch out whether you're adding or multiplying with your zeros. Well, I'm trying to find out the value of D. So I'm going to divide out by 2A. Once again, if you're having a hard time rearranging these equations, make sure you talk to me about it, and we will sort through it either at Focus or on Google Meet, depending on how we're looking for help, or how you guys are getting help, depending where we are with COVID. All right. So, ladies and gentlemen, that should be VF. There we go. So I have my values. So my VF is my 11.7. We square that value. We divide that by 2 times 9.81 meters per second squared. And then we are going to get our values of 97.7 ... is going to be our distance. Okay. So ladies and gentlemen, what we now need to do is what? How many points am I taking off here? I dropped a number. Excuse me. I am tired today, guys. I completely read this wrong. 6.9777. I forgot to write 6. My decimal in the wrong spot. How did I catch that? I want you guys to think for a moment about my mistake of just miscopying down a number there. What made me start to question? Notice I paused there for a minute. I was starting to think something's wrong with this number. Now, recall I've already done these calculations prior to filming the video, and I've just got them up on my computer over here. So, why would I question that number? I had written down 97. I wrote down 97. That is a ridiculously big number for a shelf. And I was thinking, 97 meters? 97 meters? What kind of shelf is this? Right? Is this a ball falls from a shelf, a top shelf? You don't have 97 meter shelves. Like, what's up with this? Your physics equations, your numbers need to make sense for the scenario. We're talking about a shelf. We're not going to have a 97 meter shelf. So when we look at the 6.97, okay, a 7-meter shelf. That's reasonable. We could absolutely have a really tall shelf that's 7 meters. Okay, that makes sense. So when you're doing your calculations with physics, you gotta think, does this number make sense for the scenario in which you're in? Okay? Makes a huge difference. When we get to dealing with gravity, you're going to be dealing with either teeny little numbers or massive numbers. All right? So it just depends on what it is you're looking at. But so you need to think, is this number, is it supposed to be really big? Is it supposed to be really small? Does it need to be a regular size number? So think through your numbers and see if they make sense for that scenario. That's how I caught my mistake. And I'm human. I make a lot of mistakes. That's what we do here. So sig digs, units. Now I said height of the shelf. So do I want direction? No, I did not ask for displacement. I asked for height. I asked for a scalar question. Do not give me directions on scalars. So how many sig digs do I want? Well, there's 3 here, 3 there. This 0 does not count because in the original question, there, I didn't say 0, I said drop, so it implied 0. So there is no sig digs with that. So I need 3 sig digs, so I need to round. Now this is very important, guys, especially when it comes to numerical response questions. I don't like numerical response. They're annoying because you can do everything correct, round wrong, and get the whole thing wrong. But that's how the diploma exam people do it, and because I have to give you guys diploma exams because that's what the government of Alberta decided, and that's how we got to do things, and the government of Alberta decided that numerical response can place written response, which I think is dumb. But because that's the case, they will give you 0 points on a numerical response question if you round wrong. So therefore, in order to prepare you for this, if you round wrong on a numerical response question, I'm not going to give you guys points on the test either. Okay, I think I give like 1 freebie, right? Throughout the course, if you make a mistake like that once wrong on a numerical response question or fill in your bubbles wrong, I give you 1 freebie so you can get that point back. But I give you 1 to help prepare you for these diploma exams and how picky they are. And when you're an engineer, you're rounding, life is hanging in the balance. You got to round properly. So that's why we're so picky with this. Is in the short term, your diplomas. In the long term, if you want to be an engineer, life's hanging your mouth or hanging by the edge of your mouth. So do it right. So when you're rounding, okay, I want 3 sig digs. I look at the 3. I'll go look at my 4th and 5th, 7s and 7s. Well, that's going to round that up. So I get 6.98 meters. Okay. So that is going to be my answer. Okay. All right. Now, a common question I often get in this case is, do I round this answer to 7 or 7.00? The answer is no, because this 8 is not forcing this 9 to round up. This 7 is rounding this number up to an 8. So that's okay. Let's assume, for assumption's sake, that we had 6.997. This 7 would force that 9 to round up. That would round that up to a 10, which would then force this guy to round up, which would then force this one. So then you would have 7.00 meters. Okay, so that is the case when you would round up to the next whole number there, that's 7. However, in this case, this way is correct because this 7 is not going to force this 9 to round up. Okay? Okay. All right. Ladies and gentlemen, next question. Bam! Fastest costume change in history. No. Technical difficulties. The video died partway through filming, and so we're filming on a different day now. So, welcome back. It is now a Wednesday in July, and we're going to be finishing up these set of notes on freefall. So, ladies and gentlemen, this question, both A and B, brings up some awesomely cool stuff that is also going to mean you're going to have to pay really, really close attention to, okay? So, lesson subtle hint, I do give you questions like this on your assignment, and if we are having tests and quizzes, this will be on your exam. Your next quiz, which is coming up after the set of notes, and it will be in written response. Less than subtle hint, know how to do this. All right. So, ladies and gentlemen, let's start out by, as always, making sure that we list out what it is we have and we know what we're dealing with. Okay. My pen isn't working. Plug in computer. That might help. The laptop must have been, or Chromebook must have been moved and used elsewhere since I was last filming. Okay, there we go. Now my stylus is working. There we go. All right, so ladies and gentlemen, we've got a stone is thrown vertically upward and then it returns to the thrower. So we're going to pause right here and we're going to see what that gives us. Okay, so we know thrown, Terry, once again, borrowed Freya's ball here. So you take the ball, you throw it in the air, it comes back down, it's thrown vertically upward and then returns. Now, when it is thrown vertically upward, what type of motion are we dealing with? Free fall. Okay. When we are dealing with a free fall scenario, ladies and gentlemen, what does that tell us? Gravity. That tells us that we are going to be accelerating at 9.81 meters per second squared. Okay. Now, I'm going to leave my directions until the end, until we really see what we're dealing with here, okay? And then it returns to the thrower 3.2 seconds later. And that is going to be our time, so 3.2 seconds. What is the stone's maximum height? So we are trying to calculate D. Okay. Well, ladies and gentlemen, we're missing a value. We need 4 values. What are we missing? VF. We don't know VI, but we know VF. So let's draw this scenario. Now, once again, I'm not going to draw it up and down because that's just awkward to draw. So here's the ball. It is thrown into the air vertically straight up. It is then going to reach its maximum height, and then it is going to come straight back down. Okay, so this is initial, and this is final. But if we're looking at maximum height, what are we really looking at here? What is our VF? Up here. Now remember when you take a ball and you throw it in the air, as it sits, that maximum height, for just a moment, it's got zero velocity. So that means our VF is going to be up here. Okay, and height is going to be from the ball's maximum height to from where you throw it. So we do have VF is going to equal 0 meters per second. Okay, so there's 2 things we need to look at very closely before we can even begin. Now, there's 2 things that you can do. One, you can decide that you want to make down negative, or you can decide that you want to make up negative. It doesn't really matter, but you just need to make a conscious choice about what direction you want to be positive and what direction you want to be negative here. Because we have a ball being thrown upwards. So the direction of motion is going to be up and gravity is going to be down. So we have motion and acceleration going opposite directions here. So it really, really does matter. It doesn't matter which one you make negative, so long as you make a conscious decision about it. I am going to make a conscious decision to make my down negative because my direction is going to be up and I want up to be positive in this case. Okay? Okay. So what that means is I need to expect to have my distance value as positive because that is the direction that the ball is going. Okay? If you chose to make acceleration positive and you want to make down positive, you would need to expect to get a negative number for your distance. Okie dokie? Okay. So that's the first thing we need to take care of. The second thing we need to take care of is time. What's the problem with time here, ladies and gentlemen? What's the problem with this? The time here, this 3.2 seconds, is the total time from here to here. This is 3.2 seconds from here up and then there down. So, ladies and gentlemen, where does this maximum height occur? Halfway through the motion. So when I take the ball and I throw it in the air, half of the time is going up, half of the time is going down. I am looking at the point from when the ball leaves my hand to the ball goes up here. This is the time that I'm calculating. The time that I have given you is double of what you need. So the actual time that we are going to be needing is going to be t half. Okay? So I like to label it as t half just so that way I have it in my head straight that this is the time I need to do. So I need to take, my 3.2 seconds, and I need to divide that by 2. And half of the time, half of that total time is going to give me 1.6 seconds. So that is the one that you are going to use in your calculations. So you need to think very, very carefully when we're going to be dealing with objects that are going to be thrown in the air about, do you need to double the time? Do you need to half the time? Like, what is that time actually meaning here? So read the question carefully and think about that time whenever you have an object being thrown in the air. Is that half of the motion? Is it the full motion? Do you need time from here to here, or do you need time from here to here? So really, really take time to think about that. Okie dokie? Okay, that's the hard part about the free fall. All right, so now we need to pick an equation. So you're going to grab your data sheet and you're going to look at those 5 equations that we highlighted in pink earlier. And you have A, T, D, and VF. The one equation that has all of these is our VFD equals VFT minus 1/2 AT squared. Okay? So you're going to plunk your numbers in. Well, let's do the easiest one first. Well, VF is 0. 0 times T is 0, so cancel that out, and that's going to give you 0. Now, be very, very cautious with this, ladies and gentlemen. I've seen this mistake done several times before. Remember, if you're adding 0, the net value stays the same. So 0 plus T would be T. 0 times T is 0. So make sure you cancel out that entire VFT. Okay? We're then going to be left with negative 1/2 AT squared. So now we have our negative. You can't get rid of that. 1/2. You're going to multiply that by negative 9.81. And you're going to multiply that by, once again, use this time, your 1.6, square that value. Okay, now you guys can probably already see where this negative stuff makes a big difference on your direction. Negative and negative is going to give you a positive. Excellent. We want a positive displacement here, or positive distance. Which is what we already predicted earlier, so that's good. If you chose the opposite route and chose to make down positive, this value would not be there and you'd wind up with a negative answer, which is okay. All right, so it just depends on what you labeled as negative. All right. So then for that, we're going to put that in your calculator and you're going to wind up with 12.5568 ... All right. For full points, we need to determine scalar or vector. Well, I said height. Oops, I'm writing vector and thinking scalar. It's Monday. Not really, it's Wednesday. Okay, so it's scalar. So I don't want direction with that answer. So, but I do want sig digs and I do want units. So maximum height, so we know we're going to be needing meters, and we've got 3 sig digs here. So I want 3 sig digs, and 9.81 is 3 sig digs. So I want 3 sig digs in my answer. Ladies and gentlemen, this 0 here does not count towards sig digs. The reason why is the value of this is implied. It's not given to you explicitly in a numerical form. And if it's not given to you in a numerical form, there is no sig digs associated with it. Okay? So 3 sig digs. All right, so we're going to need to round this number. So 1, 2, 3 sig digs. We look at this 5 and this 6. That's going to result in that rounding up. So we are going to wind up with 12.6 meters. Put a box around your answer. Communicate to me. That's what it is you want me to mark. And we're done. Okay. So we're going to go and look at our next question here. So what is the velocity of the stone when it is released by the thrower? Okay, so what we are trying to find here is our VI. So let's list out what it is we have. So we have our time total is 3.2 seconds. We have time half of 1.6 seconds. There's a reason I'm listing both of them, so pay attention to that. And ladies and gentlemen, there's 2 strategies that you can get here for your VF. So I am going to give you guys both strategies here. Now notice, ladies and gentlemen, I specifically did not list out the distance or height or displacement that this ball has gone. Why is that? Why am I not going to show you that version? Because it could be wrong. It's a concept called the multiplication of errors. So let's say you're an engineer. Let's say lives are hanging in the balance of your math. And are you going to want to be using a bunch of rounded numbers midway? No, you're not. So when we go back and look at this equation, and when you look at this in your calculator, even your calculator's value is rounded. It's an irrational number. Technically, it's going to go on forever, right? Like pi. So you don't want to go and put this in there because there's going to be errors. Even when you use all the numbers in your calculators, there's still going to be error. So don't use this. There's been a bunch of math done already to get that number. And now for your purposes in Physics 20, if you use this number and you make a mistake in B, because you use your answer from A and B, when you have another option and you make a mistake, you're going to get the answer wrong. And if you show your work properly and what have you, I might only take off half a point or something, but you don't want to do that. And if it's a multiple choice and numerical response question, you're not getting any points. So do not use numbers that have had math done on them already by you if there's any other option. And if there isn't an option, use the values that have had the least amount of math done on them. So I am not going to use displacement. I'm not going to use D at all in these 2 samples. Okay? Okay. So keep that in mind. Multiplication of errors is the thing. Now, because when people are doing like these types of calculations in engineering for a living, you're not doing like 2-step calculations. You could be doing, oh heavens, I don't know, many step calculations. And if you have a rounding error early, and then the rounding errors are going to add up. Well, little error, little error, little error, little error, little error, and it just all builds into this huge value. I experienced this in chemistry in university in one of the labs. We had to do a synthesis of an organic compound, and it was tough. We had many steps, And so we're doing all these steps and trying to synthesize a compound. And, you know, you're human, so you're not doing things perfectly. And at the very end, we had to figure out, okay, well, what percentage of a yield do you have? I had nothing. I had a 0% yield in synthesizing this organic compound. I go to I filter my final product, and I have to go analyze it, and I'm like, there's nothing in my filter. So there were so many errors in my lab procedure that I had nothing left to analyze. I had to borrow someone else in the lab sample to go analyze because I had nothing. So it shows up in actual science. So multiplication of errors, it's a thing. All right. So what are your two strategies for approaching this? So there's two strategies for VF. Okay. So this one here is strategy number 1. Okay. Now with your first strategy, I am going to go with where you use your VF as time half. Okay. All right. So this here, you could choose to use VF up here, and then VI would be here. Oopsie, I wrote it at that's the ball that's not 0. There you go. There's the ball. And then your VI would be down here. Now, if that is half of the motion, what time do you use? Oh, I forgot to write down acceleration. Now, for this one, I'm still going to make my down as positive, or positive, down as negative, okay? Because the ball's being initially thrown upward. All right. So for this one, my VF would be 0 meters per second here. So with strategy 1, I would use which time? 3.2 or 1.6? 1.6. So I have A, VI, and I've got T, and I've got VF. So my acceleration is my VF minus my VI over delta T. Now you say, but that equation isn't on my data sheet. Yes, it is. That one is this guy here, except I've expanded that delta. Remember that delta means difference in. So the difference in time, the change in time. So final minus initial, I've just expanded out that delta. Alrighty, cool beans. All right, so now I take my VF, which is 0, my VI, my VI, which I'm trying to find. You know what, let's actually be smart here and rearrange before I start plunking numbers in here. So I am trying to get my VI. My VF is 0. So I can honestly just cancel that out right now. But remember, 0 minus VI is going to be negative VI. So my acceleration is equal to negative VI divided by time. Okay, so I multiply time over, so AT is going to equal negative VI. Well, it's kind of annoying to have that negative 1 there, so I'm going to multiply each side by negative 1 in order to get rid of that negative. So negative AT is going to equal VI. All right. Okay. So my VI is going to equal negative of negative 9.81 multiplied by the time of 1.6 seconds. Now notice, ladies and gentlemen, this negative is going to make a huge difference. I decided earlier that I wanted down to be negative, so that means anything positive is going to be up. The question asked for velocity. Okay, what was the velocity? So it means a vector. So it's going to be extra important to know what your signs mean as for the direction. So you're going to put this into your calculator. Negative of a negative is a positive. So you're going to get a positive number here. And once you plunk all of this into your calculator, you are going to get 15.696 ... Okay. Your final answer, this is a vector. Direction, sig, digs, units. So when you go back up to the question, there are going to be your 3 sig digs. So let's get that out of the way first. So there's, you're going to go 1, 2, 3. There's your 3 sig digs. You look at these next ones to round up. That 9 is going to bump that 6 up to a 7. It's velocity, so your units are meters per second. And I said vector, so I want direction. So that means you need to put up. And the fact that that number is a positive number tells you that it is up. Sounds good? Okay. Alrighty-o. Let's look at method number 2. Now, method number 2 is going to involve looking at the entire trajectory. Okay, so that would be using the total time. So the total motion of the ball is where the ball goes up, it stops at the very top, and then it goes down. In Physics 20, the curriculum states that we do not factor in air resistance. In reality, when I take this ball and I throw it in the air, there absolutely is air resistance, 100%. But that's not part of the Physics 20 curriculum, okay? So, assuming no air resistance, we have our VI here. That means all of the energy that I initially put into this is going to go up, turn into potential, turn back down into kinetic. So that initial velocity is going to be the exact same as the final velocity, but opposite direction. So what that means, ladies and gentlemen, is our VI is equal to negative VF if this is going to be your VF. Or VF is equal to negative VI. It doesn't really matter which way you go about it. I have chosen to make up positives. Because I've chosen to make up positive, I want my VI to be positive because VI is up and VF is negative. Okay, so VF is down. So my VI is upwards. My VF down here is down. Because we're leaving out friction and air resistance, that means VF, so your VI is equal to negative VF. Well, how does that help us? A lot, actually. Okay, we can do some lovely math wizardry and solve this via substitution. Okay, well, if VI equals negative VF, well, we would then have VI, we're trying to find VI, we have VF, and then we have our time. Now, what time would we use here? T half or T total? T total. Good. Because we're looking at this to this. Okay. Okay. So, ladies and gentlemen, let's look at our same equation. So VF minus VI divided by T. VI is equal to negative VF. Okay. That means VF is equal to negative VI. Okay. Okay. I want to find VI. I am going to take this VF and I am going to substitute the VF for the negative VI. So, negative VI minus VI divided by time. Okay? Okay. So now I have negative VI and negative VI. What can I do with that? Combine them. So, using the algebra skills you have developed in math, you're going to take this negative VI minus VI, and you are going to get negative 2 VI. Look, so you got the two terms that are identical. Negative VI and negative VI. There's two of them. You can combine them. Divided by time. Now look at this. This is looking pretty similar to what we have over here, except we got a negative 2 to deal with. But guess what? We divided by 2 earlier when we got t half. We're going to get the exact same numerical value. Okay, so I'm now going to isolate for VI. I am going to multiply by time and divide by negative 2 on both sides. Okay, so that's going to cancel. My VI is going to then equal my AT divided by negative 2. I plonk in my numbers now, remembering that I chose down to be negative, so that means I need my A to still be negative, so negative 9.81 multiplied, make sure you're using that full time, 3.2 divided by negative 2. Negative divided by a negative is a positive. So we are then, once you put those numbers in your calculator, guess what you get? 15.696 ... which you then put into appropriate units, sig, digs, and direction. All right? Okay. I know the stuff is tricky, ladies and gentlemen. Spend some time with it. And the two big things to focus with freefall. Watch the time. Because there might be some times, that I'm only going to give you the value for half of time. I may give you t half. And then you may need to make the conscious decision to double the time. So whether you're going to be dividing by half or multiplying by 2 is going to depend on the scenario. So read the question very carefully. Okay? Okay. So, ladies and gentlemen, what we've got here are a bunch of practice problems for you guys to work on. Those are out of the workbooks you guys will have got back in September. Or start of the semester, we'll say, because heaven knows when you guys are actually going to be watching this, even though I'm filming this in July. So do a bunch of these, do enough of them to make sure that you are comfortable with this topic. This is the end of the chapter. After this, it is COVID. So whether we have tests or not, I don't know at this point. The government just released yesterday that we're going back in September, but I don't know what's going to happen. So if we have tests and quizzes, then you have a quiz after this. And regardless of what is happening with COVID, you have an assignment due after this now. So get that assignment done. Make sure you know what your due dates and that kind of thing are. Check with me. And ladies and gentlemen, have a good day. Do some practice problems. And then no fires, injuries, or explosions. All right. So have a good rest of your day. Watch out for rampaging viruses. And we'll see you later. Now I can't find the stop button. You think after all this filming, I would figure out how to stop filming. It won't stop filming. There we go. Talk to you guys later. Bye.